So how are we going to represent these char pair nodes in C? Before we get into the actual code, let's talk about what it is we're trying to represent. Well, we've got two kinds of nodes, right? So if we think about the types of nodes that we might have in our program, there are going to be two types, right? There's going to be a pair type. And a pair type of node is going to have two entries in it. And the two entries are going to be node pointers, right? So the left node pointer and the right node pointer. Right? And what does this point to? Well, this points to some other type of node. It could point to another pair, but for this example, let's imagine the other kind of node, which is a char node. And a char node is only going to need to store a single character of data. So let's say the char A and the char B. Right? And so these are the values of the char nodes. Right? So our nodes have a few properties. Right? They have the property of what type of node is it, as well as what is the data in that node. Right? And the data in a pair is left and right. Both are node pointer. And the character value, maybe the data we'll call C, and it is just type char. Right? So how can we represent this in code? Well, the first thing we should probably take on is this type problem. How do we represent two different types? Well, we're going to use an enum for that. So I'm going to say typedef enum node type. And node type will be the name of the enum that we specify. So just like structs that have their own namespace, and this is super redundant in the case of an enum. In fact, I'm going to remove that name enum here. What we're saying is we're declaring an enum, and we're going to put at the top level of type names in our type namespace the name node type, or the symbol node type. And an enum for node type is going to have two variants, right? A pair node or a char node. Right? And so we've defined an enum for node type. And I should mention, I'm just working in a Scratch file. This is an empty C file that we're not even going to run. I just want to work towards how do we actually represent this in code in a meaningful way. So now that we have this enum named node type set up, let's declare our struct. And I'm going to do something slightly different than we've done in the past here. And I'm going to forward declare this struct. So typedef struct node will have the name node. Now remember, with structs, they have their own namespace. So the struct namespace, or the struct node, is what we would have to use unless we declared a top level type. And we're doing that with typedef and saying a typedef node is the same as a struct node. Okay. And now that's a forward declaration of using a typedef. And now we're going to actually write the definition of, well, what is a node? So I'm going to say, what is a struct node? And we've already seen that a struct node has a few things, right? So it has a type. And what is its type? Type's type? Well, it's node type, right? That's the enum that we had set up. So a node either has to be a pair node or a char node. And now we need to take care of its data. So what are the two types of data we can store? Well, if it's a pair node, then we're going to have a node pointer for the left and a node pointer for the right entry, right? So left and right are both pointers, right? Now, if it's a char node, we're going to have character data, a single character, and we can just name that C, okay? Oops. And great. So now let's set up a really simple dummy main function that makes use of this and tries to reproduce the structure that we had illustrated out. So we're going to need, let's start from the bottom up here. Let's hand code some char nodes. So we're going to have a node of A, and A.type is going to be a char node, and A.c is going to be, the character for A is just A. And we're going to have a B node. B.type is going to be a char node. And B.character is going to be the character B. And lastly, we're going to have another node type, and I'll just give it the name P for short for pair. And p.type is going to be a pair node. P.left is going to be the address of A, and p.right is going to be the address of B. Okay. And so the node A would correspond to this care node, the node B would correspond to this care node, and P to the pair that we've set up above. Now, I want you to pause the video here and think for a moment whether you see any potential issues with what we've set up here. Consider that all four of these field values, or all four of these member values, type, left, right, and C, ask yourself, what are those four values for each of the nodes that we set up down below? So we've got a little problem, right? There's some waste that's happening here, right? And there's a little bit of unsafety because we don't really know, we didn't initialize left and right in either of these cares, and we didn't initialize C in the pair. So we've got some uninitialized data, and we don't really know what the values are for those. So we've got some uninitialized data, but we also have some memory waste. So let's talk about the memory waste real quick. I'm going to switch back over to pen here. And if we think about the layout of a node, what is it made up of? Well, it's made up of a node type. And this enum has only two variants. So if the compiler was trying to be clever about it, it could have used, let's just say 1 byte to hold the node type. Now we've got two node pointers and 2x of these. So each node pointer on a 64-bit machine is going to be 8 bytes. So we've got 16 bytes for node pointers. And we've got one character value for our character nodes, and that's 1 more byte, right? Now, this example isn't going to, either a node should take 17 bytes in the case of a pair node, or it should take 2 bytes in the case of a care node, right? But ours are always taking 18 bytes. And we're going to look at a way to, in C, makes it such that we're never going to use more than 17 bytes, right? It seems pretty silly that we would ever need more than 17 bytes. We should never need more than the ability to store a pair node because we know that we're only going to ever have one of these, right? We either have to have 2 nodes, pointers, in the case of a pair node, or a single care, right? It has to be one or the other of these. It will never be both. So we're going to take a look at a union type in C that allows us to achieve that, right? And before we get into it, what I want to remind you of is the definition of our grammar here was a node is either going to be a pair or a care. And we can think of this as a union, right? A node is the union of a pair or a care. And we're going to be able to express the same concept in code using something called a union in C. So the first thing I want to do is put a name on the types of values that a node can be. Right? So the first type of node value is going to be a struct that is a pair value. Right? And what is a pair value? Well, a pair value is made up of a left node pointer and a right node pointer. So I'm actually just going to cut that and paste it right in to this pair value definition. And the name of this type that we're defining is a pair value. Right? So a pair value is made up of a left and a right node pointer. And a care value then is just going to need to hold a single character. Right? So I'm going to rewrite this to be type def care and care value. I didn't need to do this. This is being somewhat pedantic, but I'm trying to be intentional about creating some consistency between these two concepts, right? So if a node value is either going to be a care value or a pair value, how can we express that in C? Well, this is a new concept we haven't explored before, and it's called a union type. So a union is going to say that, okay, the union of a pair value, and I'm going to name this pair, or a care value in this union, which will be named value, because that will be the type of data, we'll be accessing that data directly, is going to be named node value. Right? And this corresponds one-to-one with the concept that we explored in our grammar, where we had, right, a node value. Node is either going to be a pair, which is what our first option in this union is. It's either going to be a pair or it's going to be a char. Right? And I chose not to use the word char here because that's a keyword in C. We couldn't have used just char. So we're just calling the char value the actual value of a leaf in our tree. Right? So there's a one-to-one correspondence there. And lastly, what we need to do is say, okay, well, a node is made up of a type and a node value named its data. Okay? So notice we've got a type a node is made up of its type, which will tell us, is this a char node type or a pair node type? And then its value is going to be the union of either a pair value or a char value. A union can never be both of these things. It can only be one of these two things. Right? And it will be up to us to decide which to use based on the type of node we're dealing with. So now that we've defined this union and this different member of our node struct, let's actually go refactor our code below to be sure that it actually works. So now we can no longer say a.c, right? So node doesn't have any member named c. Node has a member named data, right? And data can either be a pair value or a char value. And in the case of the char value, it's just value, right? So when we say a.data.value is assigned a, what we're saying is the data member of the node struct that's named a in this function, it's being assigned a character value for its union of the data member, right? So data is going to store just a single character a. It's not going to store a pair value because we are assigning to it the character value a. And same idea with b. Right? So what about this pair? Well, I'm actually just going to start over here. So when we say p.data, well, we know we're working with a pair, right? And a pair value has two properties to it. It's a struct with two members, right? So its left is going to be the a node, a reference to its address in memory. And then the right side is going to be the address of b. Right? Now this looks pretty verbose, right? But let's break this down. So what we're saying here is when we access the pair node p's data member, data is a union type. And so we need to decide, well, which variant of this union or which type in this union are we working with? Are we working with a pair or are we working with a value, which is a char value, right? Well, we're working with pair, right? So when we know that we're working with pair, we know that pair is going to be of type pair value. And pair value is either going to be, is going to have two members in it, right? So a pair value has a pointer to two pointers to nodes left and right. And so we access those members of that struct here. So what's the big win here? And why did we go to this trouble? Well, now node is only going to take up the least amount of space it needs. It's never going to need to be able to hold both pairs and chars in the same struct. So what do we mean by this? Well, if we think about the node struct, it's going to have a nodes type. And the node type is going to be 1 byte, let's say, right? The compiler might choose to do something else here, but we know that we only need 1 byte in order to store it. Now, what about this node value? How much data does it need? Well, the point of a union is to say that this union node value is either going to be a pair or a char. And a pair node, we learned, needs, or a pair value needs 16 bytes. It's made of 2 pointers, right? And a char value needs only 1 byte. So the size of a union type is going to be the maximum size of any single variant of it, right? We never are going to need more than 16 bytes to store a node value because we know that it's only either going to be one of these two things at any given time. And so what the compiler will do is choose, okay, well, we're going to choose to reserve 16 bytes for this. So in the case where it's a pair, we'll use all of those bytes. But the case where it's a char, what we're going to do is if we imagine we've got 16 bytes for our value reserved, we're just going to choose the very first byte of that space to store the char value, right? So that was the char named value that we had set up. And that would overlap with where we would store the pointer for 2 pairs if this were a pair node. And that's okay, because it only is ever going to be one of those 2 values at any given point in time in our program. And that's something that we are guaranteeing as the programmers making use of a union type in C. So the purpose of a union is to say, hey, this is going to be a value that has to be one of many different types depending on the use case. And here, this is a simple node type where it can only be one of 2 types of values, but you could imagine, and in today's example, we're going to see that there's a third type of value, which is an error value that will have an error message of type char pointer to a string. And in a real language, you could imagine nodes of with even more types to them. And the union says, okay, well, there's going to be one of these types that we're going to store is going to have the maximum amount of space. That's all we should ever need. We should not need space for all of these different types for every single node that we're going to store, because that would be wasteful, right? It's only going to be one of these types at any given time. So we'll reserve enough space to store the biggest one. And then whenever we use smaller ones, we'll just use whatever space we reserved in order to fit the biggest one for there. And there will be some amount of waste in that scenario, but we wind up thinking that's okay in most conditions. So this is how we're representing a node. We have a struct with 2 members. The node type is an enum, and it has to be either a pair node or a char node. And a node value is a union. And that means we're going to be able to store 2 different types of data accessed by this data member. And then depending on the type, we're going to use a name to specify, well, which type of data are we accessing here? And this is a common strategy for achieving the ability to have multiple different types in a single node or a single struct in C.